So for the part two, we want to do a current control once again, but in this case, we're going to use a given model of the PMSM from specialized power systems of Simscape. So as input, we have three electrical signals. Those should be a three-phase voltage. And as output, we have 16 different measurements. In this case, we measure the A, B, and C currents. It is to mention that we can directly measure D and Q currents, but we want to make it as close to the reality as possible and use the transform. So these three currents are put together in a single vector and pass through the Clark transform. So we go from ABC currents to alpha beta zero currents, and then once again through the Park transform in order to get the rotational currents. Here we do need an angle, and this angle will be the rotor angle that is measured here. We get the angular speed of the machine. Once again, we could get the angle, but again, we want to do like a real process. This speed is integrated in order to get the angle, and the angle is passed through this Park transform. So once we have the D and Q0, DQ0 currents, these are separated, and both the D and Q currents are compared with their respective references. For the D current, we want to have always keep it in zero, and the Q current will be changed with a step. So the errors are passed through a PI controller. We have the constants for the T current controller, here for the Q current controller, and these outputs are put together once again in a vector in order to do the inverse process. It is to mark that all these transforms have also a third component, and that's the zero component, and as it can be intuitive, it will always remain zero. This is why this zero current won't go through any controller at all. So the inverse Clark transform, we get the alpha beta system. Once again, we need this angle that is the same angle as before. Then through the inverse Clark transform, and then this ABC system is separated in order to get the electrical signals with this special plug from Simscape. The torque is the same as the ones used in part one. This means it's proportional to the square of the angular speed. So we are going to put a final value of 3. After 3 seconds, we're going to simulate 10 seconds. Here we have this scope in order to measure the DNQ current. And okay, we can see that we have 3 values. The D current with yellow color, Q current with blue, and zero current with red. The zero current always remains in zero. The D current wants to stay in zero. It gets a tiny oscillation after this step. And for the Q current, that is the current that we want to control. After the 3 seconds, it gets this step, it gets close to 3 and oscillates a bit. And after that, it remains in the desired value. If we now change the value, let's say 10, and simulate again, we'll see that the dynamics are pretty similar. An oscillation, and then it goes to the final value.